Good afternoon, everyone. Hope you are doing okay. Uh, so today we continue where we left off yesterday. So what we did yesterday was abstracting, further abstracting types and functions, and we practiced the kind of the steps of the abstraction process on a few more things. The last example, if I remember correctly, in this section was that we drew a bunch of random stars over a sky using process of fold, and that's where we stop. So just a reminder, what we defined as process, what we kind of derived as a useful abstraction of a very repetitive pattern that was happening is actually defined as foldar in the uh, ISL library. So if you look at the documentation for intermediate student language, you can find foldar over there. Uh, as I said, there is also a corresponding foldl, but we don't look at it just yet. But foldar, here's basically what foldar does: is whenever we stumble upon cons, we replace it with an application of the operation that we are applying, combining it with the result of applying the same process to the rest of the list. Finally, if we find an empty case, if we have an empty list, we just replace it with the base, and we call it foldar, even though we start, of course, from the left. So we go into the list from the left. When the things start getting combined, we start from the innermost, right? We combine the last element with the base, then the penultimate element with that, then the third element from the end with that one, and finally we combine the first one with the result of that. Okay, so just a recap about this. Any questions about foldar or the generic signatures that we introduced yesterday for list operations? Okay. So today we'll look at a few more patterns that are kind of recurring, and how we abstract them, how we apply the abstraction process to them. So let me start by a motivating example here, or two examples. So let's say that we want to design two functions, right? One function is that a function that squares each element of a given list. Right, so applying square to each given list. If we get a list 1, 2, 3, 4, 5, we should get 1, 4, 9, 16, and 25. Hope my math is right. And then let's design another function that calculates the length of each string in a given list of strings. Okay, so if I give it the list of hello world, yes, no, I expect to get something like 5, 5, 3, and 2 back. And in both cases, if I have an empty list, there's nothing to return. So how do we design let's start with the square function. It's pretty simple with what we have so far. Any suggestions? Josh? Can you speak up? Yeah, so since the input is a list, right, we can start with a con for the two cases of a list. If we have an empty list, we do something. If we have a cons list, we do something else. What do we return for the empty case? Straightforward, yep. This one's just the empty one. What do we do in the cons case? So here, if we follow the template, we have a first, of LON, and then we have a square all combined in some way of rest of LON, right? Yeah?
So just const the first square and then the rest, first square of the rest.
So we just const the square of the first element with whatever we get from processing the rest of the list. Okay, it should work. What's the signature for this function? Yeah?
Takes in a list of numbers and outputs a list of numbers.
Yeah, this one's simple. Takes in a list of numbers and returns a list of numbers. So these two will fail, but the first two check expecs should be okay if I didn't introduce typos. Okay. So the two check expecs that failed are for length all, otherwise we're good here. Let's do the second function. What's the signature for this one? Josh? This one takes in a list of string and outputs a list of number. Okay, so since we have a list again, I'll just save you the trouble of shouting out, use the template. We have something here. If we have a cons, we do something with the first one and then do get the rest. Okay, again, what do we do for the empty case? Yeah? We return an empty. Easy peasy. The cons case, yeah?
First, the def con instead of con.
Where? Oh yeah, thank you.
Then is there like a string to number?
Yeah. So we want a particular number for a string, yeah?
The cons the string length.
So string length is the one that gets me string length. I const the string length with the length of the lengths of the rest of the lists, the rest of the list singular. Let's see, and all tests pass. And again, as you were all waiting for me to type basically the same two functions with some differences, you might be wondering, okay, what do we do about this one? How can we save this guy all this typing that he's doing right now? So what are the differences between these two functions? Yeah?
So one difference is like the function is used on the first of whatever the list is.
So the function, here we have SQR, so this one over here, and we have string length over here, right? Anything else that's really different? Yeah?
The square all outputs the same as the first list, but like all changes in the string to
So the difference between them is that a list, the first one just takes a list of number and returns a list of numbers, and the operation that we apply is an operation from a number to a number. The second one takes in a list of strings and uses an operation that takes a string to a number, so string length, and the function overall takes a list of strings and returns a list of number. Okay, so the signature is slightly different. The operation that we apply here is different, and in fact, there's a relation between the operation that we apply here and the type of the function. But otherwise, the code is pretty much the same. So we might want to derive a generalized version of this. Okay, so how do we do that? What are the common things? First, how do we call this one? Any suggestions? Yeah? Do all? Yeah, that's one. We could do all because we are doing an operation for all the elements. We could do that. We definitely need to take in a list, right? What changes between the two functions? Yeah?
The operation.
The operation, right? So that's slightly different here. Okay, but otherwise, if I use the same approach, right, taking here the operation is different, so we change that one. Still applying it to the first element here, calling the recursive function list and applying the operation. Right. So we abstracted. The only thing that we actually abstracted is the operation here at this point. And now we will fill in the signature in just a little bit. So if I have this function, and provided that I define my this way, define my, what am I talking about? Yeah, I don't know. I forgot how the sentence ends there. But so the first thing that it will shout to me about is that I'm using a function before I define it. So how can I redefine square all using do all? Should be relatively easy, Josh.
You process all listed numbers.
I do what?
You process all of element square.
I don't have process all.
Oh, I thought we were redefining the first one. Oh, sorry, do all.
Do all, yeah. All, what's the operation here?
Square.
Square. And the list of numbers, right, that I get in here. Now if I rerun the check expects, still okay on this one. And the same way, if I want to redefine length all, what's this one? Yeah?
Be do all,
Mm-hmm.
and then string length, LOS.
Length LOS. Okay. Again, checking that I didn't change the behavior. Still okay. Okay. So again, we have a function that's general, that allows us to pass in any operation and apply it to any element of the list. Yeah, we do, in theory, need check expects for the do all function, but I'm skipping them in the interest of time. And in particular, especially if I check my do all function properly, then I don't need to have many check expects for the derived functions. But what I want to do now is to get to the type signature of this function. Right. So we take an argument two arguments actually and return something. What is the type of the list that we take in? Josh? List of X, right? So main reason we are writing a generic function is to be able to pass in a list of anything. So we have list of X here. What is the type of the operation? So we have a list of X. We are applying it to each element of the list. So that would mean it needs to take in an X and return, Charlie?
It returns some Y.
It returns some Y, right? With square all, we had the same types again. So if we just looked at this example, it would be okay to think like maybe we just have an X to X operation, right? Take in the same type as it returns. But for length all, we are actually converting the type of the list. We are changing from a list of string to a list of number, and the operation determines that. So we have an operation of going from X to Y. And finally, based on this, the return type is, yeah?
A list of Y.
A list of Y. Okay, and again, I need to say that X and Y are just some variables that I use here. They are not some predefined types from before. Okay. So one way to look at the signature of this function is to think, okay, so the types are fully determined by the type of the operation that I pass in, right? If I pass in an operation that goes from string to number, then I need to pass in a list of strings, and I get a list of numbers, right? The other way of looking at it is okay, if I pass in a list of strings, then I need a function that at least takes a list of strings, right? Whatever it returns will be then determining the return type. So you can kind of think about it in multiple ways. Also, the context that I use this function in, right? Here, what is expected from this is a list of Y, so that means that I need to get a list of Y. I pass in a list of X, so that I need some function that converts from X to Y. Okay, so you can always kind of think about what do I have and what do I need, and kind of fill in the blanks from there. Any questions about this function? It will be unsurprising to you that, again, this is a very, very common pattern of processing lists. So the function that we just defined is actually predefined in ISL. And traditionally, these functions have the name map. Okay? And what it means is when you just read the argument, it says map the operation over the given list. So map the operation to each element. I need to comment it out because it's predefined, and just change my things here. Still working. Okay. So mapping an operation to each element of a list is another powerful abstraction. And just to kind of hammer it home, what the difference between folding and mapping is, I'll do the same thing that I did here for fold for map. So if I start with, if I map a function, we don't have a base over a list, right? So something that's constructed from consing elements until we get to an empty one. Sorry. then the result of this will be, well, the first case of map just keeps the cons and applies the function to the first element. Right? And we map f onto the rest of the list. Then for the next element, we map f over that element and continue. Okay. Again, map over the third element, continue with the rest of the list. Finally, map over the fourth element. And map over the empty list. The empty case is just returning an empty. So return that and we are done. Okay. So while fold basically replaces each cons with an application of the function and base and the empty list with some base value, map keeps the structure of the list. It preserves the structure of the list. It just converts each element using the function. Okay. There's a question online. So is the return of foldr not a list then? No, it's not a list. The return type of foldr is exactly the same type as the return type of f, which is the same as the base type. Okay. The difference between foldr and map is, while foldr is basically summarizing a list as a single value of some kind. Sometimes it's also called reducing a list using some operation. Map is preserving the structure of the list, just converting the elements, okay, or processing it element by element. Map takes a list, returns a list. Foldr takes a list and returns some other value that's, in some sense, is a summary of what the list is. Any other questions? Yeah, Josh?
I don't know if you highlighted this, but I was just looking at the contact phase.
Fine? Okay. Anything else?
What is base?
Base is the value returned from foldr. So from foldr for the empty list, right? So foldr was a function. If we look at the body, it's right up here. If we have an empty list, we simply return the base. If we have a cons, we apply the function to the first element and fold the rest of the list. Okay. So base is the base value that is returned from foldr. Okay. Moving on. Actually, no. Let's not move on just yet. Let's do one more exercise just to see that we are all on the same page. So let's say that I want to design a function that adds, for example, 4 to the length of each. No. Adds 4 to each number in the list. Right? So I want a function that that is 4 to each, taking in a list of number, since we are only adding 4 to each element, we also get a list of numbers back. When? How do I define this? Max?
Map,
Mm-hmm.
and then, parentheses plus 4. Oh, okay.
Uh-huh. So that's the question. Charlie?
So I think you're wrong, but I think we have to go and define a method that takes a number, returns that number plus 4, and then we can plug that method into that function into the dot 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 in our map function.
Exactly. So the problem here is that this needs to have a type number to number, right? We have an operation. Plus takes 2 arguments at least. It's a little more general than that, but we treat it as just taking 2. So we need to define something that helps us achieve what we need. So we need an add 4 that has a number to number signature. So it just takes a number and adds 4 to n. And this, then it works out well. Right? Good. Now, what if I want to do add 1 to each? Yeah?
It would be the same as add 4, except you use add 1 because that's predefined.
Yeah, so this one's easy. That's predefined. So if I do add 1 to each, I'll just use add 1 and I'm done. That's already predefined. Okay, how about Max?
Yep. For add 4, exceptions, add 42.
Yeah, so we need to define a new function add 42 and which adds 42 to n, and then I can just use the same same principle here at 42 at 42. Repetitive, right? So how about I want to define add x to all, and I want to give it an x and a list of numbers so that I can add the given number to each element of the list. X to all. So I'm attempting to abstract the repetitive pattern that I'm doing here, right? The only thing that changes here is the number that I'm adding. Every time I change the number, I need to define a new function so that I can use map. How can I do this more generally? Any ideas? Yeah?
Add x function, just call it.
Okay, so I define an add x function, which does
Take the same,
Okay, and adds them together, right? So then I use it as map add x to LON. Yeah.
Like add X, over into it, that way it is right now, like it is begin X. Have add X begin X, is that allowed?
So something like this, or
Doesn't have any.
so we can only pass in a function, right? What I wrote there was already an expression. The problem with this one is that we have an x which takes in a number and a number and returns a number, which doesn't solve a problem that we need a function that takes in a number and returns a number. So how do we do this? What we really want is to be able not to mention this x as in the argument of that x, right? If only we had a way of making this x be available to this function, right? So something like I have defined x42, then at 42 is simply defined as this, right? Because now this x comes from here, that's 42. I'm getting the result. But we want it to change with whatever the x is passed into this function. So how about we try to do something like this? This is kind of what we want, right? We want to define a function that is aware of what the x is from around, so that we can just have it take a single argument so that it fits the signature for map, and we should be okay. Now I cannot just paste the define in like this. I need another piece of syntax, which is where we were going all along. Yeah, so you all were almost right. We don't have lambda, so we cannot do lambda right now. But we do a local definition of a function. And the way local works is that we can give it any, I will delete this, any definition. Okay. And that definition that I place in here will be local to the expression that comes as its last argument. So right now I'm saying locally define add x, where add x of n is adding x to n. And I'm using it in this map expression. Because x is defined just before I do the local definition, this x is already available inside of here, right? So I'm kind of capturing the x inside of this function. That allows me to have only one argument to x and pass it in as the appropriate function. Okay, let that sink in a little bit. I just took whatever I can do up here right? I can define functions, I can define variables. I placed it inside of local, which makes it into a local definition, which makes the definition available in that single expression. Okay? The effect of that is that whatever I use here refers to whatever was available just outside the local definition. Let me just check that this works. And x to all 15 and to a list of 1, 2, 3, 4. And we should get 14, 15, 16, and 17. Unless I made some mistakes, we're good. Yeah?
If you try to define like add x outside of that, like what would it do? Would it care or?
If I did what I did at the beginning, so something like this.
No, if you had the local add x
Uh-huh.
there, but then you like try to define an add x somewhere else.
Right. Excellent question. So this is something that I wanted to get to. So add x, and let's say that it just adds a concrete number. So 14 to n right now, doesn't matter. The trick with local definitions, so something that we change here, right? So the question is, okay, where does this add x come from? Is it this one or is it this one? The rule that you will have to remember when you look up what definitions are is that basically to look up what this is, you need to kind of go to the left and up and find the nearest definition as you go from inside outside, right? With just having global definitions, which is all that we dealt with here, was you could easily have the approach where you just like, oh, I need to find that x. Let me scroll to the beginning of the file and just go and find where it's defined, because there was only one definition and you could refer to it. With local definitions, you need to go from where the name is used and work your way kind of to the left and up, looking for the definition. Okay? So left because it needs to appear before, and up again because it needs to appear before. In a one-line program, everything will be to the left. In a program where everything is on a separate line, it will be up, right? So that's why to the left and up. Now, the same goes for arguments of functions, right? If I had an x here, and I could use it inside of this function, right? This one refers to the x that's defined here. I go left and up, and I find this one as the nearest one. In here, this x comes from this point, right? From the argument. I go to the left and up, and this is the nearest one that I find. This one is not visible inside of this function. Okay? So this is something that you will kind of have to think about and let's dig in. Okay? Luckily for you, Dr. Rackard has this helpful feature, which if you look up and click on check syntax in the top right corner, right next to the stepper, it will do something and kind of change the color of the program. What this gives me is I can hover over any name and it will point to where it's defined. Right? So so this x is defined right over there. This at 42, its definition is right over here. If I go inside my function, this x comes from the argument to this function. This at x comes from the local definition, not from the global one. And it also works the other way around, where I can go over a name that's defined and it shows me all the places where it's used, which is also quite useful. So all the places where it's visible. This X is only visible here. It cannot reach to the definition here. Okay.
Is it generally discouraged to have global function and local function in the same name?
In general, yes, I would really encourage you to try to name things differently. Okay. In particular, having something like this wouldn't be like you would get points for this anyway, right? Because it's some X, it's used as a constant, it's lowercase, so that's not a good naming. But even with functions, I would try to come up with different names, because you want to help yourself and kind of avoid those errors where you go to the left and up, but overlook some definition maybe, and then think that something else is happening. So I would strongly encourage you to come up with different names. And this is related, so there's another question: do we need to write a design recipe for local functions? For local functions, you don't need to use the design recipe. There's also one consequence for local functions that is very different from global functions. And that is that you cannot write check expects for local functions, right? Because they are only visible inside of this function, and a check expect has to appear somewhere outside, I cannot test this one. The consequence of that is that whatever you define as a local function should be as simple as possible, so that you can just look at it and be like, okay, this makes sense. Okay, if you needed to do something more complex, define global functions that actually perform whatever you need to, give them enough arguments, and then define a local function that just uses that global function that is well tested and well checked.
Can we similarly define local variables?
Yes, so this local thing, this local construct, you can use any sort of definition that you want here, and in particular you can let me do something really dumb and say that I want to define y to be x plus x minus x, right? And then say that this should use y, for example. So now y is a local definition that actually is just x. It just created a dumb expression that I wrote it wrong. This one, right? So I can use a local definition of a variable just the same way. Okay. Any further questions about local definitions? I appreciate that nobody asked me the question that I got in the morning. So now that local definitions don't have to have check expects, can we just write everything as a local function? Just write the local and then the whole homework as a one local definition. Then be like, have check expects for my main function, right? So like, I have 3, that must be enough for the whole program. So yeah, the rule is try to keep whatever you define as local as simple as possible, so that you still can check the kind of computation. Any complex computation should be checked with check expects. Okay, so now we have another powerful tool in our toolbox, which are local definitions. So, which is nice, but also you need to kind of think about a bit more about the relation between where the definition appears and where a variable is used or where a function name is used, right? Because they don't just have to appear in order from the top to the bottom of the file, but rather can be inside of expressions. So it's a powerful tool. Use it well and carefully. Unless there are any other questions about local definitions, there are?
Index and marks for complex local functions.
Yes. That's what I was trying to say, right? If you have a complex operation, you should define it as a global one and then use an abbreviation in the local definition. Okay. Any other questions about, like, can we do this to avoid doing work and stuff like that that I need to get out of the way right now? Josh?
Another example of a function that requires a local definition.
What?
Another example
Of a function
that would require a local definition.
that would require a local definition? Phew. Require a local definition. Here's one. So we did do all, right, which was a map. Now, mapping a function to a list. Now the question is, can I define map using fold? Yeah?
Would you just say like map would be on whatever the default thing is?
So map would be, so I need to do fold, right?
Yeah. Then you have like a local
Uh-huh.
definition. Like define. Then your map, or like dummy character map.
Dummy what?
Like since we're trying to do map,
Uh-huh.
just define it as something that isn't map.
Right.
Yeah.
Yeah, so the first thing to realize is, I think that will be helpful, is that what does this do? I copy this and I replace f with cons and base with an empty list.
That would just be here. Wouldn't where every F is, would put cons there?
Yeah. So all the f's will get replaced with cons. And this one, and this one, and the base becomes the empty. Okay, so that's a useful function. Map is just a little step away from there, right? I'm still consing the same thing, except before I cons something, I still apply the function inside of it, right? So where the local definition comes in here is that I need to define damn it, cons f, right, which gives me an element, and and the rest of the list applies f to x and conses it with the rest of the list. Then I can just use cons f like this, and I define map. Okay. This is maybe a little bit too far, but I need the local definition because I need to create a function that pushes whatever is given here as an argument inside of the cons. And then I can use foldr to define a list. For a foldr of any operation, does it return each element in the list one after the other? I understand that the elements are no longer in the list, but I don't quite understand the way in which they are all returned together. They are combined with the operation, right? So whatever I pass in as the function to foldr determines what is returned. It's combining each element, starting with the base, and then going from the back of the list and combining the elements. Okay. So basically, anything that requires you to use the argument and basically take it, change something to, for example, like many of the use cases where you just want a function to take one argument, but you want to parameterize it, so you want to give it something more. You can just have a local definition that just captures the whatever is given to the function that you are defining and passing in. Okay. Okay, so we have map, we have local definitions, work nicely together to give us what we need. I think I'm missing a parenthesis somewhere. Okay. Now, the last thing that I want to do is to define a function. Again, like abstract a pattern that happens very often, and define a function that design a function that checks if each number in the given list is positive. Okay, so something that we'll call all positive. Okay, and I'll give it a list of numbers. What do I expect back? Yeah? A Boolean. Let me give a true example, and let me give a negative as well. So something like this. How do I define this function? What's the body? Yeah?
Do foldr
Okay.
with and. Or, no, we need to and like greater than 0, right? Greater than positive.
Uh-huh.
So we need a separate function for that.
Right. So define globally or? Okay. This one. So you want the local definition. What shall I name this function?
And positive.
And positive, something like this. Actually, I should name it with huh. How many arguments? 2. Okay. The first one will be a number, right? What's the second one?
List numbers?
List of numbers. Okay. What shall we do in the body?
So, and, greater than or equal to 0 for the number.
Greater than 0, right? And is greater than 0.
And then call itself on the rest of the list.
Itself. Like this? Yeah?
Instead of n, is n the first element in the list? Like what is
So I think the intention was here that we have a function that checks whether a given number is positive and somehow combines it with the previous result, right? But we kind of, I think we got ahead of ourselves a little bit. Let's yeah.
Wow, instead of taking in a list of numbers, we'll take in a boolean as the last one.
Very good. So instead of taking in a list of numbers, we can simply combine it with the result of the rest. So something like this. Right? And now we can fold. What's the base? True. And the list of numbers. Like this. Very good. Okay. Let's run the check expects. Seems to be good. Let's do another similar one. So let's do a function that checks if all strings in a list are longer than 5 letters. Okay. So longer than 5, list of strings, and just to get kind of the structure, I will do this one in the long form. I'll say if empty list, then I'll return true. If cons list, then I check whether the first one, string length of first of list of strings is greater than 5. Okay, so that would be the long form. check. So I hope this one should be true. And just to get another one. False. Okay. So these two are basically two different ways of writing down the same thing. So this was a pretty good use of a local definition and basically applying FOLDAR, checking what type do we expect and writing a local definition to get the function that we need using the arguments that we need. That's pretty good. Here's the kind of the long form where if we just follow the list template, this is kind of what we get here, right? For the base case, we return true. It's kind of a little bit hidden in here. For the recursive case, we check if something holds for the first element, and then we combine it with the rest of the elements. So if whatever we are checking holds for the first element, and it holds for the rest of the list, then the whole thing is true. Okay. And we won't go into like, okay, spot the differences and kind of abstract it. This is something that is very common, right? You check, you have a list and you want to know if all the elements in the list satisfy something, right? In particular, this positive, right, can be expressed as a predicate for a number, right? So I can define positive and s is n greater than 0, right? And I can express 5 string s is the string length of s greater than 5. Right. Any condition can be expressed as a predicate on the element of the list. Using this, in particular, we can rewrite this as 5. Okay, and this one can be rewritten as n. What I'm trying to get at is that, in particular, I think the fold kind of hides what we are getting at, but this one has a pattern that we kind of want to abstract. So if the predicate holds for the first element and it holds for the rest of the elements, then the result should be true. And this is again so useful that there is a function for this called endmap, which takes a predicate and the list. Okay. And basically does exactly what we wanted to do. So signature, which I'll fill in. Check that each element of the set is by the given predicate. Now the type of this one is a predicate will take whatever the element of the list is and return a boolean, and take in a list of x and return a boolean here. Okay. And yes, this could be defined just as well using fold and the local definition, but I still think that it's easier to see what's going on here. Now, the reason why we return true here, you can think about it as in two ways, right? You can think about this, okay, this is what makes our recursion work, because if we return false for an empty list, then even if it has some elements, that all elements actually satisfy it, it will return false in the end. So we need to return true. You can also think about it when you answer the question, for each element that I can find in the list, does it satisfy the predicate, right? I cannot find any element in the list, and that means that each element that I can find actually satisfies, because I cannot find any. There's nothing to check. And now, I'm sorry that I'm running out of time. The other function that comes, again, it's defined in the library, is one that checks if at least one element of the given list satisfies this, right? And it's called a NOR map. Uses OR instead of AND, and uses false in the empty case. Okay. So, sorry for running over, but basically I wanted to finish with these two functions, again, abstract a very useful pattern where you ask something about the list, right? You want to know if either each element holds something, so you want to know if all numbers are positive, or you want to know if at least one element is at least one number positive in this list, okay? So I'll kind of I'll leave you with that. I'm sorry that I ran over time. I hope you all have a great weekend. Thanks for coming. Thanks for listening. Let me know if you have any questions, either by emailing or if somebody online wants to post quickly, I can take them. Thank you.